to SST with its specific calibration equation. The method that we used to produce this stack was a mean-based stacking scheme with 5,000 Monte Carlo simulations. We were able to get back 278 years of data back to 1733. And I really want to draw your attention again to the last 1970 to 2012, where we have this very pronounced warming trend. It's 8.8 degrees Celsius. This warming trend is consistent with other warming trends that have been produced from the Florida Keys. Ilse Kuffner published a paper a few years ago where she sees the exact same amount of warming from 1970 to 2012. So this is just a really, really cool stack. And you can see that this interval here in the late 60s, early 70s is still present even with 4 corals. Down here I just put, so this pink was the length of my Siderastrea, the purple is the length of my Orbicella, and all of the gray are previously published data that other researchers had published from this region, and we stacked it all together, and this is what we got. So that was really cool. The next thing we did was we wanted to see, okay, we have this great stack, but what does it mean? Well, I did some digging, and I found the record of the Atlantic multi-decadal oscillation. So the AMO is a natural climate cycle. It is, the AMO index was composed from detrended sea surface temperature anomalies over the North Atlantic Ocean from 0 to 70 degrees latitude. The AMO is a really cool climate phenomenon where it oscillates between positive periods and negative phases. The positive periods have warm sea surface temperature anomalies. The negative or cold phases have cooler sea surface temperature anomalies. We care about this in Florida because the warm phases have been linked to higher hurricane landfall, higher hurricane frequency. So that's something that we really want to know and understand here. The AMO has a cyclicity of about 65 to 80 years. Problem with the AMO is the data, the observational data that was used to compose the AMO index only goes back to 1856. So that's only enough for about 1 to 1.5 cycles to really be present. So we need to have a paleo proxy and a paleo record of AMO variability if we're going to be able to look at how it acted in the past and how it's going to influence hurricanes and other climate phenomena in the future. So I found this record and I said, I have some cyclicity in my record, my stack, that kind of looks like that. So what I did was I compared my stacked record, that's here in the black, and I did running correlations between my stack and the AMO record, and we found an extremely high positive correlation. That's this figure here is the running correlation, R squared value. Here, its highest is right here, right where you see that dip in my record in the late 60s, early 70s. I played around with leads and lags, and I found the best correlation fit when the AMO lagged behind my core stack by about 9 years. Really well, correlates really well. So my stack is the record in black, and the AMO stack, or I'm sorry, the AMO index is the record in blue. Each one, the blue axes correspond to the AMO index, the black axes correspond with my stack. This was kind of surprising. We didn't really expect to see this. And then I scratched my head. First of all, I was like, this is really awesome. And then I scratched my head a little bit, and I was like, what does this mean? So I did some spectral analysis. I used MTM method, multi-taper method with 3 tapers to look at spectral analysis of my coral stack. And this is what we found. We found a periodicity of 80 to 90 years that was significant at the 90% confidence level. roughly consistent with that of the AMO. And we found a peak significant at 28 to 30 years, which is about half of the AMO cycle. So that really made me excited. I was like, yeah, I think I finally have a record of AMO variability prior to 1856. So basically, my question, did the AMO persist prior to the observational period of 1856? Well, I think the answer is yes. And basically, so now, this record, there are some mismatches, especially right around a little bit in here. The AMO index, the early part of the record back in 1856, some of that data was not quality controlled. A lot of it was from ships just putting buckets over the side and sticking a temperature thermometer in it. But I think overall that the Dry Tortugas is a really good place to look and reconstruct AMO variability. Our hypothesis, basically, because the lag didn't really make sense the first time I thought about it, but basically I have this nice figure here. Warming is going to start in the low latitudes. So basically, if the warming starts in the low latitudes, and then if that warm water gets transported from the low latitudes up through the loop current, through the Florida Straits, and then into the Gulf Stream, where it's transported up into the North Atlantic, that warming has to propagate. So I hypothesize it takes about 9 years to propagate into the North Atlantic, where that warming is then picked up and seen in the AMO index. So that was a really cool research project that was published back in 2017. I was really proud of that work. I think it was good work. If anyone wants to read more about it or ask me more questions about it, you can find it on the internet. I can email it to you, or we can talk about it after this talk. So the good thing about research is that it answers some questions. The bad thing about research is you usually have more questions, and that certainly happened in this case. So we have this great record of what we think is AMO variability from the Dry Tortugas, but that left us with some more questions. Basically, okay, we're saying that these corals reconstruct sea surface temperature and therefore AMO, but how well do the corals themselves reconstruct? How do we know that we're getting an accurate reconstruction of sea surface temperature? The other question that we wanted to answer was, in the previous study, I said that each coral was calibrated to its own independent sea surface temperature equation, its own regression. That's great, but that doesn't work if you have a fossil coral and you can't do an independent temperature regression on it. Or another reason if you don't have a modern calibration, things like that. So it would really behoove the community to have a calibration that can be applied to multiple corals of a species from the same region. So that's what we did. I had 5 Orbicella faviolata colonies from the Dry Tortugas that had an 11-year period of overlap. So I took those 5 corals, I microsampled them, I ran them for strontium and calcium, and this is the raw data. So this is how well they overlapped with each other. Some of them, this was the full record. This gray interval here is the overlap of all. This is the period of overlap between all 5 of them. So that's what I focused on. You can see the length here. I put the length of each coral on the bottom. So this period is the interval of overlap. So I used the overlapping data to produce a new calibration equation. I used the AVH-RR SST data set. That is sea surface temperature data that is available from polar satellites. It's very high resolution. We think as this point, it's probably the best sea surface temperature record to use for calibrations. It doesn't go back very far. That's the problem. If you wanted a longer calibration, it's not going to be useful for that. But we developed a new calibration equation to calibrate strontium calcium to SST. And then So we did that. That was one of the points of this study. And then we wanted to see, okay, how well do these corals replicate? Because that's really important. If you have one coral and it's telling you one thing, and you have another coral and it's telling you another thing, that doesn't really do a lot of good if you're trying to reconstruct climate. So what I did, I kind of broke I have two rules with presentations, and I broke both of them on these next two slides. One of my rules is to never show an equation, and I broke that rule. But I didn't see how else I could get this point across without showing this equation. These are x-rays of all 5 of the coral colonies that I had for the study. The squiggles are the strontium calcium records. They're not to scale. They're just for visual purposes. So I microsampled every one of these colonies, and then I looked at the areas of overlap because I wanted to see how well did the corals replicate among the same colony, and then I wanted to see how well the corals replicated between colonies. So I did 2 things. I looked at the overlap on overlapping paths on each coral. So these red dashed boxes are kind of hard to see. That was the data that I looked at for the intra-colony comparison. And then I took it one step further, and I wanted to compare all of the data between the 5 colonies. And I did it strictly using the standard deviations. We did a new method, it's called, well, it's not really new, but a statistical method called root mean square, where you take the standard deviations of your terms, you add them, you square them, you add them, and then you square root the whole thing, and you get an error term. So the 3 sources of error that I looked at was the intercolony error, the intra-colony error, intercolony error, and the analytical error. That was just the error that the ICP gave me off of the machine. And you get a number. I'm fortunately glossing over some of these details because these statistics, to get into the nitty-gritty of them, I'll be here all day. And none of you want to hear me talk about statistics all day. So if anyone has any more questions, feel free to ask me after. But that's how we determined an RMS error. And this is my second rule that I broke. I don't like when people put up figures and you can't see them. And I know you can't really see this too well, but I do want to just draw your attention. So what we did was we got that single colony RMS error. And for subannual reconstructions, so the monthly, we got an error of about 1.66 degrees Celsius. And then I also did it for mean annual. So when I took the data for a given year and used that value, and we got a mean annual uncertainty of about 1.43 degrees Celsius. So again, that's good, but is that really going to tell you a whole lot if your error is 1.66 degrees Celsius either way? So we wanted to see how many corals it would take to reduce that. We really wanted to figure out, like, where do you get diminishing returns? And what do you have to do to get a good record? Because you can't replicate 5 corals for every location. That's just not practical. So basically, I started with one coral. I started with my longest coral. I applied the RMS error to that, and then I just progressively added each coral to it. I played around with the intercolony standard deviation, and basically, take my word for it. If you want to discuss this more after, we basically concluded that you need 3 corals to converge on the correct temperature and get the replication and the uncertainty and the error propagation that you need to be really confident that you're recording the correct sea surface temperature value. So I will leave you with some conclusions. Basically, all of this work has led me to conclude that the strontium calcium paleothermometer is a good, reliable proxy to resolve decadal scale mean shifts of about 2 degrees Celsius and multi-decadal mean shifts of about 1 degree Celsius. The uncertainties in this proxy can be reduced by combining more than one colony that will generate composite strontium calcium SST reconstructions, and that Orbicella faveolata, that paleothermometer, can be used to resolve decadal to centennial temperature trends. One last thing, I got the last paper out thanks to Pam. She let me sit in on her scientific writing class. It made a world of difference to me in my writing. Scientific writing is a hard skill. It's something I struggle with, and if you guys ever get an opportunity to take a scientific writing class with Pam or with anyone else, I highly, highly recommend it. I also took Dr. Chambers' data analysis methods class, and that helped so much with my data management, my data treatment, coding. That's also a skill that I struggle with, and I definitely recommend that learn it while you can in grad school, because it's a lot harder after you get out into the real world to try to go back and learn those skills. So if anyone has any questions or about my research, or if you have any questions about advice or anything, I'll be happy to answer them. Thanks.